diagram of a cell. Talking about a electro cell, which is a battery. Right, we're basically what I'm talking about. Anytime you can separate two metals and there's an electron flow between them, that is electricity. That's how a battery or a cell works. Typically, the basic cell, backed by a guy named Volta, who's the guy that discovered it, Italian chemist, came up with this type of situation. He filled up one of two different beakers with some sort of metal, piece of metal there, and he put a different type of metal over here. The original one was zinc and copper, and he connected the two together with a wire. Now, at this point, nothing happens because there's not a pathway. The electrons try to go, but there's no return. So the electrons build up on whatever side, one side or the other, and it stops. There's no proceeding. So what you can do is connect the two with something called a salt bridge. A salt bridge is a tube, in this case a U-tube. Sometimes it's a porous cup. I've seen people do it with a hot dog, anything that has a lot of high content of a salt. Typically, the salt bridge contains potassium nitrate. That's kind of the standard for that. The metal that will become oxidized is going to give up electrons to the metal that's going to be reduced. So oxidized, reduced. The oxidization is going on at the anode. Reduction is the cathode. One way to remember that is anox, red cat. As electrons go down here, you're making the metal go into the ion, so the metal ions go into solution, which means this loses mass. That means this one, the metal is coming out of the solution, and it will gain mass. And in these solutions, typically you got to have 1 molar solutions of that ion. If this is copper, then that would be copper ions. If this is zinc, that means it would be filled with 1 molar zinc ions. So the pull of the electron from one to another is called the cell potential. And that's the pull of the electrons, how much force they have, if you will, is measured in volts, which is abbreviated V, and as defined as 1 joule of energy per 1 coulomb. A coulomb is a measure of electrons. It's kind of like the electrician's mole. And this is also given as that symbol too. And you measure that with, surprisingly, a voltmeter. When you do a comparing different things, different metals will pull, different metals will push. If you have copper here, put a different metal over here instead of zinc. Instead of electrons going from left to right, the electrons might go from right to left. So there's different tendencies of different metals to become oxidized and or reduced. So you got the standard potential, and this is measured against the reaction 2H plus 2 electrons going to make hydrogen gas. This is defined as 0 volts. Got to have a definition someplace, a starting place, if you will. Hydrogen is a gas, and hydrogen ions are aqueous. There's no metal like up above in this top one. So how can you account for that? Well, if you're doing ion to ion location, what you do is instead of having there's different things you can do. If it's a piece of metal that you can hook up an electrode to, then go ahead and do that. If it is some ions, like one ion going to another ion, what they do is they use a piece of platinum electrode. Platinum is incredibly inert as well as expensive. And that just serves as a surface catalyst, remembering that stuff. Now, if you need to add a gas, if you're producing a gas, that's okay the way it is. But if you need to add a gas, what they do is they have this special setup where they have the platinum like that, but they put a little cone, a little tube, where they put the gas inside. So if you need to add a gas, like if you were to reverse this reaction right here, you'd have to have that to put the gas in. So this is if you have a piece of solid metal. This is if you have ions to ions, something like, say, copper 1 plus to copper 2 plus. And then this is where you would have to add a gas, say H2 going to H plus, not balancing. If you are comparing to your standard to hydrogen, if you are producing electrons, compare the standard potential, coming back to this, if you are producing electrons compared to the hydrogen, then that voltage is a positive, and if you need to add electrons compared to hydrogen to get it to go, then that substance has a negative voltage. I already mentioned the 1 molar solutions up here, standard conditions. One molar solution, 1 atmosphere of pressure, 25 degrees Celsius. Under standard conditions, the symbol is the knot, the E knot symbol. You have a reduction table in your book. And this reduction table is what it does. It's talking about reducing elements. That means you are adding electrons to make another substance. And then they give you the positive or negative value compared to hydrogen here. It's a reduction table, which means you're reducing. But we all remember that there's a redox reaction, which means you got to have an oxidation. So what you do is you take this reaction here and you reverse it so that the electron is being produced. And in this case, you switch the sign. So if it's being oxidized, you switch the sign. If it's being reduced, you leave the sign the same. You do not need to balance the equation. You do not multiply by any coefficients. You just take the differences and add them up. The reason for this is it's not the number of electrons we're looking at, it's the push or the pull of the electrons, and that's independent of how much you have. Suppose you're going to make a battery out of zinc and copper. Zinc's reduction number is negative 0.76 volts. Copper is a positive plus 3 to 4 volts. So if you're going to make a battery, the voltage has to be a positive number. So this is going to stay reduced. You're going to have electrons on its side. This is going to be oxidized because you need a positive number. So you switch one of the two and you switch in the order so that you get a positive number. So what you do to find the potential is the copper is 0.34, the zinc is 0.76. You add those together, 1.10 volts. And so that's how you can determine what the voltage is. If you're not told that it is going to be oxidized or reduced, copper plus zinc ions, zinc plus copper ions, the copper is going up in charge, so that's being oxidized, so you switch that, so that's negative 0.34 for the copper, and the zinc will be reduced negative 0.76, which means that you got a negative 1.10, so doing the battery in this order will not it will not make a battery. You cannot do it that way. It will not be spontaneous. It will have to go in the reverse direction. If you reverse it, it turns to a positive. That means that the zinc has to be oxidized. So if you come up here, zinc would be on this side, the copper metal would be on that side. A simplification of drawing this stuff is line notation. If we're going to go back to the spontaneous reaction, zinc plus copper ions produces copper plus zinc ions. You always start with the anode phase, or the oxidized phase. So we already said that the zinc has to be oxidized. So you have zinc metal oxidizing to zinc ions. Two lines represents the salt bridge. And then you have the copper ions changing to copper metal. This is not balancing the equation. This is how you set up a battery. Like up in here with zinc being on the left and copper being on the right, being oxidized and reduced. So to here, so this side's oxidized, this side's reduced. You will always have a solid on the outsides, and then on the insides you have ions slash gas. If you would have a situation where you have copper and copper 1 plus ion, copper 2 plus, comma, copper plus, you have to have metal on the outside, so that's where your platinum electrode comes into play. So if you're going from copper 2 plus to copper 1 plus on platinum, electrode would be shown there. And it always has to be on the solid on the outside. This could tell you how to build a cell just from the line notation. That concludes this lesson on electrochemistry.